In the previous video, I mentioned that almost everything in organic chemistry can function as either a Bronsted acid or a Bronsted base. It's just going to depend on who it's around as to which role it could play. So what we've seen in the initial examples, all of them showed water acting as a Bronsted base. But it can also, because it has a pair of protons, it can donate one of those and act as a Bronsted acid. So let's take a look at a reaction involving that. So first of all, I'm going to write this out as an equation form, or in an equation form. And then we're going to talk about what's going on. Okay, so what are all these things? So water, we know that. NaNH2. That's an ionic compound that's called sodium amide. So amide, just like the name of the functional group. This is an ionic compound, so it's made up of sodium plus and the amide ion, which has a minus charge. Actually, let me draw that a little bit more clearly so that we can see that. So NH2 minus, there we go. So two lone pairs on the nitrogen, two bonds to hydrogens, negative charge on the nitrogen. Okay, so first of all, the amide ion is what NH2 minus is called. So this is the amide ion. And so you're probably noticing that we've seen this word amide before, and you'd be right. So amide, as you've seen, means this functional group. So the functional group that involves a carbonyl flanked by some sort of a nitrogen group. Now, I used NH2 in the example, but it could be two methyls or a methyl and an H attached to that N. Remember, there's all kinds of variation here. So amide refers to that. But the word amide in organic chemistry also means that you have a compound that has a nitrogen with a negative charge. So nitrogen with negative charge. Okay, so that's sodium amide. Now, the sodium part of this. The sodium, as we know, again from Gen Chem, is a spectator. And by definition, a spectator ion is not participating in the reaction. And so as such, if you want to, when you're drawing a mechanism, you can omit spectator ions from the mechanism. Now, some people are going to want to do that, and that's fine. And other people are going to want to have those spectators in there. In fact, in the book, it probably shows the mechanisms and so on with the spectators. So you can do it either way. I like to recommend that people leave them out because when they're in there, we have a tendency to want to have them do something. It's like, why draw it unless it's going to do something? Well, no, it's not going to do anything. It's a spectator. So you can leave it out and that's okay. We know it's in there. We know that charge is always balanced and conserved. Okay, so if we have something with a negative charge floating around, it's got to have something with a positive charge to balance it. Okay, but we do know that because they're spectators, they're not participating in the reaction, so we can leave them out. That's what we're going to do, is leave out that spectator when we draw the mechanism, which is what we're going to do now. So here's water, and here's the amide ion. Remember, the sodium is floating around in there, the sodium plus, not worried about it. In this example, water is acting as the acid. So it's going to donate one of those two protons to the amide ion, which is the base. So to draw the mechanism, just like before, we always start the arrow at the electron pair in the base that's going to be used to bond to the hydrogen. Start the arrow there, point to the hydrogen, and then the bond between that proton and the thing it's attached to, you're going to break toward that other thing. So in this HO bond, you would break the bond towards the oxygen. And in fact, pretty much any time you're breaking a bond in this way, the electrons are going to move on to the more electronegative element in the bond. So that's a general rule of thumb that can prove helpful. Okay, so let's draw the products of this. We end up with the hydroxide ion. And so now the spectator ion is going to switch teams and it's going to go balance the negative charge on a hydroxide ion. Excuse me. And then we also have ammonia as one of the products, so NH3. So let's label our conjugates. Water is the Bronsted acid. Its conjugate base is the hydroxide ion. Amidion is the Bronsted base that we started with. Its conjugate acid is ammonia. Now let's assess which side of this reaction is favored at equilibrium. So to do that, we need pKa values. So pause the video and think about what are the pKa values we need. For which chemicals in this reaction do we need pKa values? So I'm hoping that what you said during the pause, if you did pause, is that we need the pKa for water, in which case you'd be right. That pKa is 15.7. That is a number that you need to memorize. And the other pKa we need is for ammonia, the other acid in the reaction. That's 36. And that's also a number to memorize. That number, that pKa value, applies not only to to ammonia, but to amines as well. So 36 is the pKa for protons attached to nitrogen atoms in either ammonia or amines. So which side is favored? Again, it's going to be the side with the weaker acid and weaker base. We know that the acid with the higher pKa is the weaker one, and so in this case, it's the right side of the reaction that's favored. Weaker acid, higher pKa. We can also, if we know pKa values, make an estimation of the equilibrium constant for a proton transfer. And we're going to use this little equation right here. So as written, a chemical reaction has reactants on the left side and products on the right side. And that's the convention that will follow when we plug numbers into the equation. So for this example, our K is going to be approximately equal to 10 raised to the power of the product acid pKa, which is 36, minus the reactant acid pKa. Now the reactant acid pKa here is 15.7. Let's just ballpark that because we're making an estimation anyway. Let's call that 16. So this means K for this reaction is about 10 to the 20. Okay, now what do you think of that number? Is that a little number, a tiny little number? Is it a moderate sized number, or is it a ginormous number? Okay, clearly that is a ginormous number. And so what we would say about this, how we would assess this reaction, would be to say that the reaction goes to completion. Which means that you have virtually all products at equilibrium. Now, a lot of the time people will want to know, well, what's the cutoff number? How do I know when a reaction goes to completion or not? Well, it depends on who you talk to, but a typical rule of thumb, maybe something along the lines of 10 to the 5 or 10 to the 6. If you have an equilibrium constant that's 10 to the 5 or 10 to the 6 or greater, then we can pretty safely say that that reaction we would consider as going to completion. One of the things we did in the last set of notes when we were discussing molecular orbitals was to look at a set of example mechanisms and determine what the frontier molecular orbitals were in each of those reactions or reaction steps. We're going to do that now with the proton transfer, and use it to fill out some more ideas about the proton transfer as well. So let's take a look at this example here. So here's ammonia. And we're going to combine it with acetic acid. Okay. Now, if we look at these two structures, what we see is the following. In the ammonia, the nitrogen has a lone pair. So it could use the lone pair to accept a proton. But it also has protons, so it could donate one of the protons. If we turn our attention to acetic acid, we have the same thing going on. There are lone pairs that could be used to accept protons, but there's also at least one acidic proton. So how do we know in this case, or in any case like this, how do we know which of these chemicals is going to be the acid and which one is going to be the base? The way to do that is if you know a few pKa values, you can compare the pKa values. So let's take a look. Ammonia, we know the pKa value for it. It's 36. And acetic acid, we saw the pKa value for that also, but even if we didn't know its exact pKa, we know that carboxylic acids typically fall into the 4 to 5 pKa range. So let's just say 4 to 5. Okay, that's enough information to be able to tell which one of these is going to act as the acid and which will act as the base. The one that will act as the acid is the one that's the stronger acid. It's more likely to donate the proton. That's the one with the lower pKa. So it's the carboxylic acid, which means that since the ammonia is not donating a proton, now that we've answered the question, we don't care what its pKa is. It's not acting as a Bronsted acid in this equation, and so it doesn't matter what the pKa value is at this point. We just needed it to figure out who is going to be the one to donate the proton. Okay, so the acetic acid is the Bronsted acid, ammonia, the Bronsted base, I'd like to point out that it's this hydrogen, the one attached to the oxygen in the carboxylic acid, that's always the one that's going to get removed. So go ahead, pause the video, draw a mechanism to show how the base accepts the proton, and then draw the products of the reaction. And so having done that, I'd be very happy to know that you drew arrows that looked something like this. So starting at the lone pair in the base, pointing to the hydrogen that's going to be donated from the acid, and then breaking the bond between the proton and the atom that it's attached to. That gives us the following. Now the nitrogen has 4 single bonds, and so when we assess formal charge, we find that that's a positive charge. And then, of course, as we saw previously, the conjugate base of acetic acid is acetate ion. All right. So before we look at the frontier orbitals for this reaction, which side is favored and what information is missing that we would need? You are absolutely right. If you're sitting in your house screaming that it's the pKa of NH4 plus that we need, and that value is 9. So to ballpark the equilibrium constant for this, it would be 10 raised to the power of the product acid pKa, which is 9, minus the reactant acid pKa. Let's take that to be 5, because the actual pKa is 4.8, so we'll just round it to 5. So 10 to the 9 minus 5, known to the fans as 10 to the 4. So this is an equilibrium reaction. You're going to have some reactants and some products. Now let's assess the frontier orbitals. Remember that it's the nucleophile or the base that's supplying electrons to the other partner in the reaction. In this case, we're talking about a Bronsted base. So that would be the one that would be using its HOMO, meaning that the acid uses its LUMO. From here, we would just apply the same ideas that we did for the examples we saw in the orbitals packet. So as this lone pair on the nitrogen, we have to determine what kind of orbital that's in. Well, it's a lone pair, so it's going to be in a non-bonding molecular orbital. So non-bonding pairs, like lone pairs, or they are lone pairs, are in non-bonding molecular orbitals. Or you could apply the hybrid orbital label for this. In ammonia, the nitrogen is sp3 hybridized, which means that that lone pair is in an sp3 orbital. So you could say NMO or sp3. Let's put or. The LUMO. When we looked at LUMO examples previously, remember that the question was, is a bond breaking in the electrophile? We just want to slightly modify that question. The question now is a bond breaking in the acid? The answer is yes. We see that in the mechanism based on this arrow right here that I highlighted in blue. That's the bond that broke. It's an OH sigma bond. And so for that bond to have broken, that means that the OH sigma star had to be involved. So the LUMO in this reaction is the OH sigma star. Notice how you can tell this just from looking at the mechanism. You don't have to draw out an entire molecular orbital diagram for each of these chemicals to know what the HOMO and what the LUMO is in each of them. Let's think about the example we did on the previous page. That was water and the amidion. So let me just redraw the mechanism quickly. So we don't have to flip back to that page. So it looks something like this. And so again, the one that is supplying the electrons to the other one is the base. And it's the base that would be using its HOMO. The HOMO in this instance, a lone pair, so a non-bonding molecular orbital, that's what contains lone pairs, or the hybrid orbital label for that nitrogen. The nitrogen has 4 areas of electron density around it, the 2 bonds to the hydrogens and the 2 lone pairs. That makes it sp3 hybrid, and so the lone pair is contained in an sp3 orbital. Water here acted as the Bronsted acid. As such, because it's being an acid, it's using its LUMO. So the question again, is a bond breaking in the acid? The answer is yes. It's an OH sigma bond that's breaking, and so we know that the OH sigma star orbital had to be involved, otherwise that bond would not have broken. Let's look at a third example of this. And this is an example that you're going to see a bit later in the semester. So we have HCl and an alkene. Now, what do you know about either of these? Well, I'm hoping that what you know about HCl is that it's a strong acid. So I'm going to use the abbreviation SA for strong acid, because we're going to see a bunch of strong acids and weak acids, so let's just use some abbreviated labels. So this is a strong acid, which we know is an acid that's going to dissociate quite readily. What that means when you see a strong acid in a reaction mixture in an organic reaction is that you need to look around to see what's going to accept the proton. If you have a strong acid, even a weak base is going to be able to accept the proton from it. Well, the only other thing that we have in there is the alkene. And so as it turns out, it is the alkene that's going to accept the proton from HCl. The way to draw that is the following. We're going to originate the arrow at the pi bond, point to that hydrogen, and then break the bond toward the chlorine. we're going to draw the products of this, which will help us assess what's going on with the frontier orbitals and the reactants. But remember, when we're assessing frontier orbitals, we only look at the reactants. Okay, so the thing here that used its electrons to accept the proton from the acid is the alkene. So the alkene in this example is acting as a Bronsted base. Therefore, it's using its highest occupied molecular orbital. The HCl acts as a Bronsted acid. So it would use its LUMO in the reaction. So let's look at the LUMO first, since we're over there. Of course, the question is, did a bond break? The answer is yes. It's the HCl sigma bond that broke, which means that the HCl sigma star orbital was involved, because otherwise that bond would not have broken. And so then what is the HOMO in this reaction? Look at where the arrow originates, and then compare the structure of the alkene to what you end up with on the other side of the equation. The alkene gets converted to a carbocation, and what's missing from the original alkene is the pi bond. So what we did was we used the pi electrons to accept the proton. So these electrons here are the same as these ones in the product. So the HOMO in this case is the CC pi orbital. So just to remind you of the relative energies of molecular orbitals, sigma is lowest, then pi, then non-bonding, then pi star, then sigma star. So the point that I'd like to make here is that if you have lone pairs in your molecule, those are probably going to be occupying the HOMO. On the other hand, if there are no lone pairs, then the next likely candidate is going to be some pi electrons. Okay. We need a starting point so that we can think about the strengths of the acids and bases that we're going to be encountering along the way. So the first question is, how do you tell if something is strong or weak? What are the definitions of these things that you know from general chemistry? Well, from general chemistry, what they told you was that an acid is strong if it dissociates completely. And it's weak if it does not dissociate completely. But those terms are referring to the behavior of acids and bases in aqueous systems. So we can think of a strong acid, sure, in terms of a complete dissociation, and a weak acid in terms of a partial dissociation. We can also think of these things in terms of how readily or not readily they donate protons. Now, you probably learned a set of strong acids in general chemistry, and we're going to be seeing those again. So you learned at least 5. Sometimes people have a 6th one on the list. The 6th one typically is perchloric acid. We're not going to deal with that, but we will be dealing with the other ones. So the strong acids that you should know from general chemistry are HCl, HBr, HI, sulfuric acid, which is H2SO4, and nitric acid, which is HNO3. Okay, so those you should have under your belt already, and we're going to be seeing all of those as we go forward. Okay, so the next question that I have for you is the following. Do all weak acids, or for that matter, do all weak bases, have strong conjugates? So do all weak acids have strong conjugate bases, and do all weak bases have strong conjugate acids? Take a minute, pause the video, think about the answer to that question. Now, when you do this, the answer that I'm hoping you came up with is no. So it's not the case that all weak acids have strong conjugate bases. It's not the case that all weak bases have strong conjugate acids. What we can say, though, or how we can frame this, is in relative terms. What we can say, and we'd be correct, is that the stronger an acid is, the weaker its conjugate base. Now, there's different ways that you can say that same thing. You could also say, the stronger a base, the weaker its conjugate acid. Okay, so it goes both ways. Okay, so this answer, no. So not all weak acids have strong conjugate bases. Now, where is that coming from? Okay, let's go down to the bottom of the page, and I'm going to draw a little picture to remind you of something that you saw, hopefully, in Gen Chem. Okay, so in Gen Chem, you probably saw a big table of acids. It was probably in your textbook. I'm sure it was in your textbook. And so you have acids, and you have their conjugate bases. And then somewhere in there, there's going to be pK value or Ka values and what have you. And so typically what they have is that the strongest acids are up at the top, and the weakest ones, so they put them in order of Ka, are at the bottom. And so the strongest acid is going to correspond to the weakest conjugate base, and the weakest acid will correspond to the strongest conjugate base. Okay, so you have a whole table of these guys. Now, by definition, however, remember we mentioned this in the previous video, by definition, only a small number of these acids on this table are strong. So let's say that that's the ones up here. So these are all strong acids. The rest of them are all weak acids. So Wa for weak acid. And a similar argument applies to the bases. By definition, only a small number of those bases are technically strong bases. So Sb for strong base. The rest of them are weak bases. So you have this whole section in the middle of the table where you have weak acid, weak base conjugate pairs. In fact, there's another place that you saw a weak acid, weak base conjugate pair, and that is buffer systems. So a buffer, by definition, is a weak acid, weak base conjugate pair. So no, a weak acid does not necessarily have a strong conjugate base. We can only refer to these things in relative terms. So the stronger something is, the weaker its conjugate will be. What we're going to do next is develop a little table. And this table is going to contain information that I'd like you to memorize. So I'd like you to know everything in detail that's on the table that we're about to make. What we're going to do is use water as our starting point. And we're going to do two things to it. First of all, we're going to allow it to react with an acid that's strong enough that it's going to be able to donate a proton to water. So I'm just going to abbreviate that acid as H+, so just a proton, with the understanding that there really is no such thing as H+ by itself. H+, the proton, it's always going to be attached to something else, some other molecule, a solvent molecule, what have you. But we can use it as an abbreviation. So when water accepts a proton, it becomes H3O+, and the process of tacking a proton onto something is called protonation. So in this direction, we are going to protonate the water. And then we'll draw another equilibrium over here. And over here, what we're going to do is remove a proton from water. That's called deprotonation. When you deprotonate water, you get hydroxide ion. So that's the conjugate base. Okay, we know some things already about H3O plus and hydroxide. We know that H3O plus is a strong acid. We also know that the hydroxide ion is a strong base. What we don't know is very much about water at this point. However, we know one thing, and that is that its pKa is 15.7. Now, as an aside, there's some controversy about that number. Okay, some people will tell you, no, the pKa of water is 14, and there have been papers written on this, and lots of people have looked into this. Okay, so without making an assessment of which of these numbers is correct, what I will tell you is that everything that you're going to be relying on from now on in other courses is probably going to be based on the pKa of water as 15.7. Every single organic chemistry undergraduate textbook reports it as 15.7. So we're going to go with that convention, even though there's another school of opinion about it. Okay, so that's an aside, and it's not something for you to worry about, but I know that people do like to look things up on the internet, and so you might run across this, so I wanted to give you a heads up. Okay, water, by definition, is a weak acid and a weak base. So those are its properties. If water acts as an acid, it's doing so as a weak acid. If it acts as a base, it's doing so as a weak base. So what we're going to do next is make another chart directly below this, but instead of water, we're going to use this. So this is one of the functional groups you learned, and which one is that? Even from here, I can hear all of you shrieking, it's an alcohol, and you would be right. This is an alcohol. And we're going to do the same thing to the alcohol that we did to water, which is to say, we're going to tack a proton onto it. So let's draw a mechanism for that down here. So an alcohol will use one of the lone pairs on the oxygen to accept the proton from whatever the acid is. And what is the result? Well, you used one of the lone pairs to form a bond to a hydrogen. The other one is still intact, so that gives the oxygen 3 single bonds, one to R, one to H, one to H, and the lone pair, which gives this a positive formal charge. So the conjugate acid of an alcohol is ROH2+. Now let's deprotonate the alcohol. And we'll draw a mechanism for that as well. Now remember, we're going to pull this proton that's attached to the oxygen and the alcohol, we're going to pull that proton off. We're going to use some base to do this. Doesn't matter what base, we don't have to specify. Because we're pulling that proton off, we have to show this bond right here, the bond between the H and the O. So start the arrow at the base, the lone pair on the base, point to the hydrogen, start a second arrow at the OH bond, point to the oxygen. The result of that is RO minus and BH plus in this case. RO minus is the thing that we care about. And so that's that guy right there. And so now we have all of our chemicals drawn. Okay. Alcohols. The pKa of an alcohol, the range of pKa's for an alcohol, is 15 to 18. Okay, so that's the final number that you would have to memorize. And we're going to make a table of this when we're done with this page. Alcohols, like water, are weak acids and weak bases. So they're weakly acidic and they're weakly basic, just like water. Now look at the pKa values. The pK of an alcohol is ballparky 16-ish, and so is the pK of water. So they have the same acid strength. They also have the same base strength. Now we can extrapolate what we saw with the conjugates of water, its conjugate acid and its conjugate base, to the conjugates of an alcohol. Which means that ROH2 plus is a strong acid and RO minus is a strong base. RO minus, the conjugate base of an alcohol, has a special name. It's called an alkoxide ion. And that's a term that you should memorize. So we would call this an alkoxide or an alkoxide ion. You can use either of those terms. Okay, so let's scoot back up to the top of the page where we have a little bit of room to make a list of the pKa's that you need to know. So you can have them all in one place. So the pKa's that you need to know are the following: amines and ammonia, 36, water, 15.7, alcohols, 15 to 18, and carboxylic acids, 4 to 5.